Hey everybody, in this video we're going to be talking about explaining a substance's or predicting a substance's physical properties by referencing the types of intermolecular forces that substance will experience. Here we're going to be comparing CH4 methane to C6H14, something called hexane, trying to figure out or guess about which of these is going to have the lower melting point. Anytime you're dealing with molecules, which these are, because they're made of only nonmetals, that means methane is going to form a molecule, so will C6H14. The whole process has to start with the Lewis structure and the shape of that molecule. CH4 is a simple little molecule that looks like this in a tetrahedral arrangement. C6H14 is a little unique. You can see that there are 6 carbons here. And anytime you've got a molecule with a bunch of carbons, those carbons tend to form these long chains. In this case, 6 carbons in a long chain. There are other ways that they could be arranged, but if we're not given any other indication of the shape that these carbons would be in, you would just assume that they do indeed all go in this long chain. And then the 14 hydrogens just kind of get distributed around, where each carbon likes to have 4 different bonds to it. So I'm going to go ahead and fill out the rest of these bonds with hydrogens. Okay, so there's my finished hexane molecule, and all of that work was just so we could compare the polarities of these two different structures. CH4, I can see right off the top that those hydrogens are symmetrically arranged around that central atom, so even though the bonds are a little bit polar, this is a non-polar molecule. And for the same reason, in my hexane I have only hydrogen atoms. They are roughly symmetrically arranged around those carbon atoms. This is also going to be a non-polar molecule, so I can compare the net dipoles of these by saying both of these molecules will have no net dipole. And that's an important part, so I want to make sure to write that down from the beginning. That is important because for non-polar molecules, there is only one intermolecular force they're going to experience, and that is called a London dispersion force. Here I'm going to call that LDF. This is the only way that non-polar molecules can stick to each other. So if you get one CH4 next to another CH4, they might interact a little bit, and the only way that they will be doing that is with these LDFs. Same thing with C6H14. The next stage in the process is to compare the strengths of those LDFs, which is stronger, which is weaker. To do that, there's actually 2 different considerations you need to make, and I'm numbering those over on the left of the video screen. Number 1 is electron cloud size, and number 2 is chain length. You have to sort of factor in both of these things, and usually there's going to be a clear-cut one that's going to lead you to the answer. Let's start with electron cloud size. Because if you look at the types of atoms in these molecules, they are both carbon and hydrogen in methane, and then again in hexane, both carbon and hydrogen. In other words, both molecules are made of the exact same types of atoms, so both molecules are going to have similar electron cloud sizes. Maybe I'll just write that down once and reference both of these molecules. So that's good news for me right now, because that means I don't really have to worry about that, because there's no difference between methane or hexane in terms of electron cloud size. There is a rather major difference, however, in terms of chain length. My methane is just one single carbon, and its chain, if you even want to call it that, is very short. Whereas here, over at hexane, I have 6 carbons in a much longer chain, and that is a key difference that I'm going to need to talk about or think about when comparing these molecules. Let's write it down. Short chain for methane, and then a longer chain for hexane. And here's why that's important. When you've got a long chain molecule, what that means is, if you can imagine like a second hexane molecule maybe stacked up on top of this, both of these guys with those long chains have lots of surface. You could think about it as surface area, where the 2 hexane molecules can come in contact with one another. Those are kind of key points here, so I'm going to just pause a minute and write that down. The longer chain results in, we'll just call it maybe more surface to keep things simple, and that more surface allows for, well, let's call this more contact points You'll often see it described that way. More contact points where hexane molecules can come into contact with one another. All of the opposite things are true for my methane, right? That shorter chain means there's less surface, which means there's going to be less contact points or fewer contact points when methanes get near one another. Is just so I can now finally compare the strengths of these LDFs, because when you've got more surface, more contact points, that's going to lead to stronger, at least more, London dispersion forces, and that's going to be true for my C6H14. Here, where I've got less contact points, that's going to lead to weaker London dispersion forces. And now, finally, I can make my final prediction about the property in question, because now I know that hexane molecules are going to experience these stronger attractive forces, and anytime you've got stronger attractions between molecules, that's going to cause certain things, certain properties to probably be true, like your substance might be a liquid at room temp, it might be a solid at room temp. A lot of properties are going to be elevated. You might see higher melting points, higher boiling points. Another common one is enthalpy of vaporization. In this particular case, of course, we're talking about melting point. So I can predict probably that hexane is going to have the higher melting point because of those stronger LDFs, whereas my methane is going to have the lower melting point because of its weaker LDFs, and I've got my prediction set. Which substance is going to have the lower melting point? Probably methane. That also wraps it up for this video. Thanks a lot for watching.